Hello everyone. Finally, we will start working on a quantum algorithm. So the algorithm we are going to talk about is named after two scientists named Dosh and Josa, and it was the first quantum algorithm that was giving us exponential benefit. That means that the classical algorithm, the classical analog of this algorithm, took exponential time to solve the problem. I mean, you had to run the query exponential times as it is increasing with n, and with the use of quantum techniques that we have understood for the last few weeks, we will show that this problem can be solved in a polynomial time, or to be more precise, with just one query. Let's hold on and try to understand. All right. So this was published in 1992. So the rough statement is a balanced versus constant black box problem. Okay. So how does it work? Let's see. So the input of first, it is thought of as a black box. So it works, and what it does is that you give it a binary string of n bits. Okay, this is f. This is a black box. All right, you give it some binary string bn, which bn means that you have n bits in the string. All right, so if you consider b2, then you will have 0 0 or 0 1 1 0 or 1 1, either of these fours. Okay, so one more thing to understand here is that how many elements do you have in bn? So obviously for the first element you have 2, the second element you have 2, and it goes for n bits. So you have 2 to the power n elements, all right, in bn. So this is the thing you have to keep in mind. And the output for this black box, or sometimes it's called oracle, the output of this black box is b, which is either, it's b means b1, that means it's either 0 or 1. Okay, so you give it an n bit string and it gives you a one single bit as an output, and that is how it works. All right, so now there's a promise. The promise is that f is either a constant function. That means that no matter what you give in bn, it will always give you 0, or it will always give you 1. Okay, you're not sure about it, and it's either a constant function. It can be always mapped to 0 or always mapped to 1, but only one of them when it's a constant function. Okay, and the second, or it can be a balanced function. That means that 50% of the times it will give you 0, and 50% of the times it will give you 1. Okay, so you're not sure how f works, but you know that it's either a constant function or a balanced function, nothing else. All right, so the problem is you have to find out whether it's a balanced or a constant function. Okay, so let's try to understand it classically first. Obviously, so let's try to solve it classically first. Classically, if you want to solve it, then what you get is that you at least, so for a bn, you have 2 to the power n elements, right? So if it is a constant function, it will be constant for 2 to the power n elements. But if it's a balanced function, then it will be 0 for 2 to the power n by 2 elements, and 1 for 2 to the power n by 2 elements, right? You have to split it into 2 parts. So the query complexity, that means the minimum, at the worst possible case, that means that the worst number of possible tries after which you are 100% certain that how many, whether it's a balanced function or a constant function. So let's say the first, you give it some random string, it gives you 0. It again gives you 0. Let's say you have, okay, let's say n is equal to 3. Okay, then you can have at most 2 cube, that is 8 elements. Alright, so let's say that in the first you give it some random bit, let's say that is 0 1 0, you get a 0. Then secondly you give it 1 0 0, you get a 0. Similarly you give another, you get a 0, and then again you give a 0. Are you still sure after 4 queries that you are getting a constant function? No, because still you can get 1 here. Alright, and then other 3 1s again. So that is balanced. So after even 4 queries, you are not sure whether it's balanced or constant, right? Or yeah, it can also happen that you just get 0 in the first one, 1 in the second one. Then you're sure that it's balanced. It's not constant. And if it is not constant, then it is promised to be balanced. Alright, but the worst possible case is you have to check it at least one more time than the half of the size of all the strings, right? So what I mean here is that the query complexity to solve this problem is 2 to the power n by 2 plus 1. So this is the half of the times, and if you do it once more, then you are 100% certain. With 100% certainty you can say for all the cases that whether it's a balanced or a constant function. Alright, so the query complexity, what you can see, is exponential in n. Why? Because this is some powers in n. If you keep on increasing n, it will increase exponentially. This is the definition of exponential, where n is in the powers. Alright, so classically there is no way you can solve it in a polynomial time. Okay, but what we will show in the next few minutes and working out quantum mechanically, that you can do it only with one query. That means you will use the black box only once, and you can say that. Okay, this is like mind-blowing. All right, because I mean classically, which is an exponential problem, you can do it only with one query. Doesn't matter how many n's do you have. Okay, so let's try to understand it quantum mechanically right now. Okay, so now let's work it out quantum mechanically. So quantum mechanically, what we are going to do, we will define this black box as UF. Okay, this is just a notation to denote the black box. So UF is a map from x, y. I will define what every part means, and it maps you to x times y XOR f of x. Okay, so now you have to understand what it is. All right, so this is the input register, okay, and this is the output register. Okay, and what it does is that this consists of n qubits, and this consists of 1 qubit. You can obviously guess why this is n and this is 1, because remember that our map was from Bn to B, right? So from n bits we were going to 1 bit. So quantum mechanically we are going from n qubits to 1 qubit. All right, and that is why this is the output and this is the input. All right, and what it does is that it keeps x as it is but changes y. So what is f of x here? F of x is the map, right? Because you give it some Bn, it will map you to some B, right? So let's say from the example, let's say it was 0 0, and 0 0 0 is mapped to 1. Then f of 0 0 0 is actually 1. Okay, so this is the n-bit string, but f of x is a 1-bit string. It's a one bit. Okay, and it depends on the map f or u, whatever you call it. U is a quantum mechanical oracle, and f is the function that we are trying to determine whether it's a constant or a balanced function. Okay, so we will have to draw a circuit, and you have already done some tutorials on circuits. So we will start. So you can already see that I'll need n qubits here and 1 qubit here. Okay, so let's try to draw a circuit. So you will initiate, as Soumitra already explained it to you, that if you initiate a qubit, it will always be in the 0 state. All right, so you start, you take n bits here, n qubits. Okay, and there is one more qubit. So this is the n qubits that is part of x, and this one is 1 qubit, 1 qubit, and this is y. Okay, so all of them are in 0 states. So now what we want to do is that I want to create an equal superposition of all the elements of Bn from this part. Okay, how to do that? Let's work out an example. So let's say that I give you 2 qubit system. All right, now what you can do so that it will turn into a superposition of all 4s. What I mean by that, it will turn into something like this: 0 0 0 1 plus 1 0 plus 1 1, and the coefficient will be 1/4. Sorry, half. Okay, so how can we do that from this? By some gate operation. Obviously, what you can do is you can already understand that this 0 0 is nothing but 0 0 like this, and it's a tensor product. So what you can do, you can act with h cross h on 0 tensor 0. Okay, and if you do that, you will obviously see that this h will act on the first qubit, and this will act on the second qubit. So what you get is 1/√2 0 plus 1/√2 1, and similarly, if you tensor product, the second one would be the same: 0 plus 1/√2 1. All right, and now if you do the product, then you can see easily that this is nothing but 0 0 plus, okay, I don't need to write the half every time, so it will be nothing but 0 1 plus 1 0 plus 1 1. All right, so you can see that by applying Hadamard gates on zeros, you can find the equally probable superposition states. I mean, equally probable superposition of all the possible states. Okay, so what we are trying to do, we are starting from zeros, and we are trying to do it as a sum over all x, where x belongs to Bn. Okay, so this is what we are trying to do. So I think it's clear to you by now that if we apply Hadamards on zeros, and if I apply a Hadamard on each zeros, then it will turn into an equal superposition state. All right, for n qubits. So let's do that. So if I want to turn it into a equally possible this is the power of quantum computing, that you can create all the possible states in one shot in a superposition state. You couldn't do it classically. All right, so what we do is that we apply Hadamards on each state. Okay, each qubit. So what we can see is that in this position, it's equal superposition of all the states, all the possible states in Bn. Okay, I hope this is clear to you, or otherwise you can ask me in the live session. And what we want to do, we want to turn this 1 qubit y, which is also in the 0 state, in the minus state. By minus I mean this one, 1 by root 2 0 minus 1 by root 2 1. Okay, in the minus state. So you already know, you already did in your tutorial how to turn a 0 state into a minus state. That's pretty easy. You apply okay, let me draw the gates in green. So this will be X, and then you need a Hadamard, then it will turn into a minus. Okay, at this point, so let me write it in the notation. At this point, your state is 1 by square root of 2 to the power n, and X belongs to Bn X, and you have this minus state. Okay, so this is your input register, but now you have all the elements necessary to check the oracles. That means that you have all the elements of Bn in a superposition state by just applying Hadamard gates. Okay, you can already see that for the input register you applied n Hadamard gates, and for the output register you applied 1 Hadamard gate and an X gate. All right, so what else? Now what we want to do is we want to apply the oracle. So I'm just writing it in a red box, but what it does, this is just UF. Okay, it should be capital. This is nothing but UF. Okay, so what does this UF do? UF, okay, let's ignore the factors of 1 by square root of 2n because we won't need them. So what it does is that, let's say that you have some X, and this minus state was nothing but 0 and minus 1. Okay, because this is the minus state. I'm ignoring the factors of square root of 2's. I don't care about them right now. So what it does, it maps it to X, as I have already defined that it doesn't change X here. X remains as it is, but it will change Y. Okay, so what it will do is that on the minus state it will just give you f of x here, because f of x XORed with 0 will just give you f of x, and it will give you a minus sign 1 XOR f of x. All right, because this is a linear map, so I want to say it, I mean you can divide it into two parts, and then the first one will be mapped to x and 0 XOR f of x, and 0 XOR f of x is nothing but x and f of x. Okay, so this is the first term here, and similarly you can do it for the second term, and you will see that you'll have a 1 here, just nothing else. Okay, so I hope this is clear to you. So what we did is that we turned it, oops. So what we did, we turned it into equal superposition after the green gates, and then we made it go through the red box, which is the oracle, or the black box that we are trying to find out whether it's balanced or constant. Okay, so what happens next? This, you can see that this thing on the right hand side is equal to x will stay as it is, and it will be 0 minus 1 if f of x is equal to 0, right? F of x can be either 0 or 1, but we don't know whether it's constant or balanced. But what we know is that if f of x is equal to 0, then the first term will be 0 and the second term would be 1, because 1 XOR 0 is 1. Okay, but if x, and I'll have a minus sign and have a 0 and a 0 minus 1 if f of x is 1. How? Because the first term will be 1 and the second term would be 1 XOR 1, which is 0, and you take a minus on the common, then you get this exactly. Okay, so the most crucial part here is this minus sign. Okay, and that is why we needed this minus state here. If we were taking the plus state, there wouldn't have been this minus sign, right? You can check it by yourself. So in the end, what we can say is that our result is nothing but minus 1 f of x to the power f of x, and you have this x and you have this 0 minus 1. So minus 1 to the power f of x means that when f of x is equal to 0, this is plus 1, and you just get this state out. And if f of x is minus 1, then you get a minus 1 here and you get the second one out, marked with the red in the minus sign. Okay, so now what have we done? Now one more thing to notice is that the inverse of h is h itself. By h I mean the Hadamard gate. Okay, so if you act on a state psi with h squared twice, you get psi back. Okay, for example, you act on 0 with h, you get plus, but you take h plus again sorry, then you get 0. Okay, and you can prove it for arbitrary states, because h square is nothing but identity. Okay, you can check it by yourself because you know the Hadamard matrix, so you can check that h square is nothing but identity. Okay, so at this point, so we were drawing this circuit. After this point, after going through the oracle, your state will be nothing but this. Okay, this is just an extra sign on the initial state, nothing else. Okay, so what I am trying to do is that I will act on okay, let me draw it with green again. So I will act on h again. And now I will not need this extra output qubit anymore. Why? We will see that. So what I'm trying to say is that I'll discard. I will not care about this qubit anymore. Okay, but what I'm trying to say is that after going through these Hadamards, you will go back to the initial state as before. Okay, so if this is a constant function, then what you're going to get, let's check that. If f of let's suppose if f of x is constant, okay, if f of x is constant, then what you're going to get in the end, because h square, if you act on h twice, it will give you the same state. So you started with n zeros, you will end up with n zeros. Okay, you will end up with n zeros if f of x is 0. If f of x is 0, because you will have no sign here, then let me use a different color, then this thing will go away. It will just give you 1, and then you'll just get this x again, and you get all the zeros. But if f of x is 1, if f of x is 1, you're going to get nothing but a minus sign and all the zeros. If f of x is equal to 1. Okay, if f of x is equal to 1. So what you can do is that you can perform measurements here in these qubits. Let's do it in pink. So you can perform measurements in all the qubits in the computational basis. Okay, and if the output of your measurement is always 0 in all the qubits, then you can certainly say that it is a constant function. All right, and now let's check if f of x is balanced. If f of x is balanced, then what you're going to get is, let me give you an example in the 2 qubit system. Okay, so okay, let's work that out. If it is 0, if you are dealing with 3 qubits, then it will be 0 0 1 and 0 1 0 0 1 1, and similarly for 1 0 0 1 0 1 1 1 0 1 1 1. Okay, so now if you had a constant function, then for all, if f of x were 0, then you would get pluses for all of them. Okay, and then you act on the Hadamard twice, then you get back this state. Okay, if f of x was equal to 1, let me use a different color for that, then you will get a minus sign for each base. Okay, minus 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 minus. Then if you act on Hadamard gates n times, what you're going to get is a minus sign before, but you're still going to get zeros, and this is a global phase, so this is not a problem for us. But if it were balanced, then what happens? Let me use the red color. Then half of them will be plus and half of them will be minus. So let's say that this one is plus, this one is minus, this one is minus, plus, minus, plus, plus, and minus, the red ones. Okay, and now if you act on with the Hadamard gates, you're not going to get the 0 states. You're going to get some state which is which depends on the explicit position of the minus and the plus signs. Okay, but you're not going to get zeros. We can only get all 3 zeros when all of them are plus or all of them are minus. Okay, so after this measurement, this pink measurements, if you can find out that you have at least one non-zero output, then you are definitely sure that this was balanced. Okay, so I hope this is clear to you, and if it is not, then please don't hesitate to ask me in the live session. All right, so what have we done? We have found whether f is balanced or not by doing this, by manipulating this circuit. So how many operations did we do? Before, classically we were doing 2 to the power n by 2 plus 1 operations. That means we had to use this black box that many times. But now we just use this black box once. Okay, along with, how many gates did we use? We had n Hadamard gates plus one Hadamard gate more, one X gate, and then n Hadamard gates again. Okay, so you in total you have 2n plus 2 gates and this oracle ones and n measurements. That's it. And it has turned into a polynomial problem, or even to be precise, you just have to use the oracle once. Okay, and then you know it with certainty whether it's a constant function or a balanced function. It will be a constant function only if all these pink outputs here are zeros. If even one of them is 1, then you are certainly sure that it's a balanced function. All right, I hope you enjoyed this session, because this is one of the fundamental examples of exponential betterment of the query complexity. That means that classically it was an exponential time problem, but now with the use of quantum mechanics we can turn it into a polynomial time problem, or to be more precise in this example, you just have to use the oracle once. All right, this is an outstanding achievement of quantum mechanics, and there are many more algorithms like that, and if you're interested you can learn it by yourself. Okay, so I hope you enjoyed it, and if you have any questions, please don't hesitate to ask me. Thank you so much.